Alright, let's continue from where we left off. Now yesterday we talked about the concept of specific heat capacity for any substances. So I try to give you a list. Now we've done half of it, so we keep on going. Now we only list 3 different substances. One is water, one is iron, the cheap metal, one is gold, expensive metal, right? Precious metal. Now, for every one of those 3, they all can have 3 physical states: solid, liquid, and gas. But for the iron and the gold, the metals, their melting point and boiling point temperatures are very high, and then so under room temperature they are solids. All right, they are not possible to form liquid and the gas. So we put solid on here. But for water, we do have 3 possible physical states at different temperature scale. All right. So we all know the solid ice and melts at 0 degree, and also the icy water frozen into ice at 0 degree. So the 0 degree is the transition temperature between the solid and the liquid H2O, right? And for liquid water to be vaporized into steam, that's a 100 degrees Celsius. Or if you are not familiar with Celsius, you should by this time. We go by Fahrenheit, and then the freezing point for icy water going to solid ice is 32 degrees Fahrenheit, and then 212 degrees Fahrenheit is the boiling point for liquid water to be vaporized into steam, the gas, right? So these 3, why I have to list all 3? Because we are here today, we're going to talk about term, specific. Now, why this term has to be there? The specific heat capacity means the heat capacity for different substances as well as the same substance with different physical state will have different values. Alright, so that's what we are so picky about it. We try to emphasize it. So let's give you some idea of the value. Let's go to calorie first, because you are more familiar with calorie instead of a joule. But also on the second column, the next column, I will give you the value for a few of them with a joule. But the only difference between is the conversion between calorie to joule was 4.184, right? So here the value for solid ice for the specific heat capacity based on the definition, right? Amount of thermal energy, which is heat right here, right, is going to be 0.5 calorie, shorthanded, right, per degree, or per gram, per Celsius degree. Now these 2 both are denominators, okay? And what is about what? Half of that value in joule, right? So equals, let's just put equal down there. So divide by half, so it's going to be 2.092 joule. Agree? Right? That's the ice. For liquid water, go by the definition of calorie, which means it's 1 gram water raised by 1 degree require exactly 1 calorie. That is the same as a specific, or you can say that definition applies to the definition of the specific heat capacity for liquid water, right? That's the same. So it's only 1. You can put a 1.0 if you want to. It doesn't make too much difference unless you insist the measurements involve significant figure. We already talked about detailed in chapter 1. So that is going to be 4.184 joule. Now let's put sign the unit in the parentheses. All right, that makes clear. Then what is gas? Gas is neither 0.5 nor 1. It is smaller than 0.5. The value for steam is 0.48, not 0.5. Same calorie gram per degree, which is, now you find out, use your calculator, right? 0.48 times the 4.184. Now, that's the value in joule. Now, what is the iron? The iron is very small. Iron value in calorie is 0.11. Now, same thing, calorie per gram per degree. For gold, all right, let me put here the gold, because our run of time is 0.0033 calorie per gram per degree Celsius. Now that is for gold. Let me put here, because handwriting is out of control with the size. All right, so that's, now, what is value? What these value tells us, right? I say specific. Look at it. If we talk about a compound H2O, the chemical formula H2O, 2 hydrogen atoms combined with 1 oxygen atom give you the water, right? And it has 3 physical states, right? Each of which have a different value, right? The steam has the lowest specific heat capacity, and the solid ice has slightly higher. The water has almost twice of both of them, right? And the value of the heat involved in calorie to be able to raise 1 gram of each by 1 Celsius degree, all right? So, seem to be among these 3 substances, including their different physical state, the value for the specific heat capacity, the highest one goes to what? Goes to liquid water. Now, think about what a specific heat capacity can do, right, to our life. Because the water we consider has almost the highest value of energy required to raise 1 gram of water by 1 degree Celsius. Consider it has the highest specific heat capacity among almost all other substances. So the water is able to, the liquid water, is able to take in 1 calorie, right, for 1 gram water, only raise the temperature of that 1 gram water by 1 Celsius degree. But the same amount of heat, right? If we apply same amount of heat to iron, the iron value is right here, right? Iron value is 0.11. Iron value is 0.11. Let me put the arrow so you see where it goes, right? This one goes to gold, solid gold. This one goes to the solid iron. Iron, the symbol in chemistry is Fe, because, and it's not English. And the gold is Au. Now that's the water, of course. That's where everybody should know, right? So compare with the 2, right, substances, right? Of course, at different physical state. If you have 1 gram water, you only need 1 calorie of heat or thermal energy to raise that 1 gram water by 1 degree Celsius. But to the same amount of heat applied to 1 gram of iron, a piece of metal, right? It is able to raise temperature by 9 degrees, because what? Raise 1 degree only need 0.1. 0.1 out of 1 is almost 1/10, which is 0.11 is the 1/9. So 0.11, 1/9 of the amount of 1 calorie is already raised temperature for 1 gram of iron metal by 1 degree. Then if you give 9 times higher energy, which is 1 calorie, right, raise 1 gram water by 1 degree, you are able to raise temperature for the iron, 1 gram of iron, right, by 9 degrees. So that's 9-fold, 9 times higher temperature. Now think about the situation, all right? In the summer, for instance, you finish your work, come home, right? Say you have a second shift, not night shift, the second shift, from 6 o'clock to 2 o'clock. The 2 o'clock is the hottest time during the day, either summer or winter, right? because the solar energy concentrated and trapped inside the atmosphere and cannot go away, and then after 8 hours of sunshine from the morning until 2 o'clock in the afternoon. So 2 o'clock or 3 o'clock p.m. normally almost always is the highest temperature during the day, right? So you come home when you're tired and then you want to take a dip in the swimming pool, right? And cool yourself off, right? Cool yourself off. And when you swimming around or just soaking there for a while, you think you are kind of relaxed and recover a little bit. You want to go back to your house and take a nap or have some meal. Now there's two choices for you to get back from the land, from the swimming pool, the water. In the swimming pool, always at one corner there is going to be a ladder. All right. Let's say the ladder is made of iron, the metal, right? And that was a clear sunny day, and then the temperature is high in the summer. It's going to be like a 95 degree Fahrenheit or 35, 36 Celsius degree, almost the temperature of the body, human body, right? It's hot and humid as well, and then that's one way you can get off the water and go back home. Or you can just hold the edge of the swimming pool, which is concrete or tile, the ceramic tile, and then flip your body and get on the land and then walk away, right? Now, which one are you going to choose? You're tired. You just barely recovered. You may say, I will choose the ladder. Well, go ahead, try it. Go ahead, try it. Because the ladder, the swimming pool, the water, the concrete, the tile, all are under the same sunshine and receive same amount of energy from the solar ray, right? So it will heat up. Now, remember this. Iron. Iron has the small specific heat capacity, then smaller one, then water is 9 times smaller. Try to recall if you have ever touched a hot piece of metal in the summer. Alright, is that going to burn your finger? So you try to hold the ladder and the rail and the step by step going up, but the time your hand will be burned, right? So that is probably not the best way to get back to the shore to go to the house. So my choice would just hold the tire. The tire will be still because the tire is not going to have very small specific heat capacity. We don't have the value here, but it's going to be larger than iron, right? And then you are able to hold it for a longer time and flip your body and then roll up and then stand up and go. So that's the difference, right? So that's why. And also, right? Let me ask you a question. If you have, now we talk about analogy. In learning science, we do not just throw in the equation, throw in the definition, and throw in the value units and ask you to read and understand by yourself and plug in and solve problem. That is not the way to learn science. Learning science, right? You have to put your brain there. And also, it's better to put your common sense in there, right? You are already a person lived on earth more than 15, 16, 17, maybe 20 years longer, right? So you have already had enough life experience. You try to connect your common sense with the life routine and the life experience when you read scientific textbook, and then try to apply those science concepts into whatever you already have experience with. If you cannot, the teacher does it for you, if the teacher is good, right? So that's what I'm doing here. So another question I ask you, if you can answer. For a house, you know, the property house builder, right? They build a company. They build 2 properties, 2 houses, exactly same, same footage, same material, same style, same number of bathroom, same tile and same shingle, whatever, the same size backyard, front yard, right? Exactly the same. One is built in a inland area, there's no water nearby. Say Raymond, right? Say Clinton, back to Boston, or somewhere, you know, in Louisiana, no water around. And the one building there. The other one built next to the Barnett Reservoir in Jackson. Right next to the water, the lake shore and the water, you know, the lake shore line, you know, maybe only about 100 yards away. You build a house down there. Exactly same. Now, which one, answer that question. Which house will sell for high price? Right? I'll give you 5 seconds. You will say, okay, yeah, of course. The house built next to lake shore, next to water, will sell for high price. Now ask yourself another question. Why? Why the house exactly same for this, everything same, sold much higher, maybe twice as higher as the one exactly same building Raymond, no water around? You say, okay, because the water around, you know, give you a lot of good scenery and you can enjoy the view. No, that is not the right answer. That is actually a baloney, and I will tell you this is not the case. What is the case? Well, let me tell you something about this Barnett Reservoir. It's a lake. It's a huge lake. Compare a beautiful lake in China where my wife came from, and they call that city called Eastern, or it's called Oriental Geneva. All right, a beautiful lake. A lot of tourist attractions and historical sites, and thousands and thousands of people visit there every day. All right, so this lake right here has nothing. Right, has nothing. Only a couple boats and then fishing catfish. Right, that's all they do. It's not as beautiful as you thought. To give you some pleasant feeling every day, you look the same thing. To me, it's gonna be dull. All right. So what is the reason? The reason is not the scenery. It is the water. Why? The water gives you the comfortableness every day. All right. In the summer, hot temperature, the sun coming down, and your house is next to water. The water has the highest, the liquid water, right? Highest specific heat capacity, 1 calorie per gram per degree. What's 1 gram of water? That's the mass. But by volume, it just happened at 4 degrees Celsius. Water has a very specific relationship between its mass and its volume. It is 1 gram of liquid water occupies exactly 1 milliliter, or we shorthand call 1 cc. cc stands for initial of cubic centimeter, but we do not use cubic centimeter to describe liquid for density. So the cc or milliliter, 1 milliliter of water is exactly 1 gram. That's 1-to-1 ratio. Very, very few will have this kind of conversion, right? But it's not conversion. We're not talking about the same entity. One's mass, one's volume. They're not conversion, right? The relationship. Anyway, so the whole lake. How many milliliter? How many gram of water? Man, that trillions, zillions, right? So every one gram of water, liquid water, will absorb 1 calorie, and it go deep, and then the heat will transfer through the water molecule down deep. Of course, go under is going to be cooler because the thick water will block the sun ray, right? Gradually getting weaker. So you get it. But the transfer of heat between liquid water will hold water inside, you know, as deep as it can go until the sun sets. Correct? All the heat will be absorbed by water. And then the wind blows to your property all day long. The breeze. The pleasant breeze. Alright? And then what's the consequence? The consequence or the results, the outcome is going to be very low electric bill for you to pay every month for the gas, for your heating in the winter, and for the air conditioning for your cooling in the summer. That's the major reason for the house built along the waterfront is much more expensive than one built in dry in the land. And also the land, you know, the price for selling the land, each acre is much different. It's so different. As I remember, I was in Oklahoma, and then the land over there sold for like, that was 1990, 1991. It was like $3,000 an acre. I don't know how many dollars, 10,000 or something here in Mississippi. But in Oklahoma, that's a dry land, so hot in the summer, so cold in the winter, and flat, right? No mountain, no here, no tree, all red soil, right? Yazoo clay type of soil is very, very dry and is not comfortable at all. So that's what the reason here. Now we understand this. Now think about this. If you wear shorts or mini skirt and then you sit on the, you have lunch, if you want to sit on the hood of your car parked outside under the sun, you don't want to, because why? It'll burn your skin, right? That's why, because the metal has a very low specific heat capacity. It's easy to transfer the heat from the source to everywhere. So the entire car, even one corner being hit by the sun, another part, the rest of the part of the car was in the shade, is going to get heat passed through the hot spot to the cold spot very quickly. Alright, so that's the reason the metal getting so hot. Alright, now we understand this. So that is the specific capacity. We talk about specific because different physical state and different substances will have a different value. Now it is two different for specific. Alright, specific, two different. Okay, now if we understand this, then we are able to find out how much heat will be involved if we have a certain amount of substances and try to raise a certain amount of a degree, right? So let's erase a little bit the board, right? All right, and we do some kind of exercise to get. Oh my God, my board was cracked. All right. That's okay. It's a board. Try to put here, not too stable. Alright. Alright. Now, if we just pick up water, because it's 1 calorie is easy, or 4.184 joule. Alright. Let's do some exercises. Alright. Let's find out. Alright, the amount of thermal energy or you call heat, that's the same, that's layman term, and is required, right? Require to raise the temperature of a certain, now I'm not going to give you a fixed value, we're going to practice, see, we'll understand orally, certain to raise the temperature of certain substances. Let's put here certain number of grams, certain number of grams of a certain not certain. You know, water. Let's just put water. Liquid water. Yeah. We just said use liquid water, right? Liquid water. By a certain degree in Celsius. All right. Now we talk about liquid water. Oh, liquid water, yes. Liquid water. Let's just water. Let's put the water here. L means liquid, alright? By a certain degree, alright? So let's start from here. Use this, right? The liquid water has a specific capacity as 1 calorie per gram per degree. Means what? If we have 1 gram water, we want to raise temperature by 1 degree, right? How many calories do we need? 1 calorie, correct? Now let's go to second set of number. If we have 1 gram water, we want to raise the temperature of the 1 gram water by 2 degrees. How many calories? 2 calories, correct? And then we can keep on going. 5 gram water raised by 1 degree, right? Oh no, 1 gram water raised by 5 degrees, right? We go degree change first, and then we need 5 calories. Then we can go, if we want to raise 1 gram water by 100 degrees, how many calories do we need? 100 calories, correct? All right. So then, if we have 1 gram water, right, raised by 1 degree is 1 calorie, and 2 gram water raised by 1 degree also 2 calories, correct? And 5 gram water raised by 1 degree, it could be 5 calories. 100 gram water raised by 1 degree will be 100 calories, correct? So if we understand that, it seems to be those values, the mass and the degree of temperature increase or decrease, will involve the energy will be a multiple, right? It's a multiple, which is the products of multiplication of these two terms, the number of grams and number of degree, correct? So you understand this, then we are able to give you a equation. The quantity Q for thermal energy, QE. Alright, I use this symbol all the time. It's very clear. There's no confusion. Sub means energy. Alright, and we haven't introduced what kind of energy this we call it, or what kind of heat we call it. We're going to get in there in the near future. Alright, so equals, seem like a mass, right, in gram, right? 1 gram, 10 gram, 100 gram. And then you have to apply 1 calorie per the specific heat capacity, right, of water, right? Let's put a bar here and the liquid water, right? In this particular case, gotta be water, right? Liquid water. And then you have to find how many degrees we'll try to raise from 0 degree to 1, or 0 degree to 5, which is 5 calorie or 1 calorie, or to 100, right? So it's going to be multiply the change or increase or decrease of temperature, the temperature change, right? And then here, the temperature change must be our T final subtract T initial. Just like you talk about a weight loss or weight gain, you always the final tomorrow's weight subtract today's weight to find the difference. Either the positive value you increase the weight, you gain weight, or negative value you lose weight. This is the same thing here. Now this give us this gram, and this is going to be what? This is the calorie. The units are going to be calorie over gram over temperature Celsius degree. So here will be in Celsius degree. Now that's the equation we are going to use to find amount of energy involved temperature change, which the temperature can be measured. Now at this moment time is almost up, and we're going to give you the term for this kind of heat involved temperature change, right? But the physical state stay in the liquid without changing the physical state. This kind of heat we call sensible heat. So next section, all right, is called sensible heat. We're going to start from here. All right, and time is up, and then I'll see you next time, next section.